Hey, welcome to The Explainer. Today, we are going to pull back the curtain on a huge part of science and data, inferential statistics. And I want you to forget about dry math formulas for a minute. Think of this as the art of making brilliant, educated guesses, using just a little bit of information to tell a story about a whole lot more. This quote, it just perfectly nails what we're talking about. We have this super detailed map of one tiny piece of the world, that's our data. But our real goal is to use that one little map to make a smart prediction about the much bigger, unseen world all around it. And that leap, well, that's the magic of inference. Okay, so to really get that leap, you've got to understand that statistics is basically split into two halves. One half is all about describing what you can see right in front of you, and the other, more exciting half, is about predicting what you can't. So on one side, you have descriptive statistics. This is the world of certainty. If I ask for the average score for your class of 30 students, that's a hard fact, right? But the second you use that average to guess the average for the entire university, you've just crossed over into inferential statistics, the world of probability and, yeah, really smart, educated guesses. So, how in the world do we make that guess? Well, probably the best analogy I've ever heard is thinking about a chef tasting a giant pot of soup. I mean, they don't drink the whole thing to see if it needs more salt, right? They just take a single spoonful. And that simple, everyday act, that is the core logic behind almost all of inferential statistics. So let's just nail down these terms, using our soup analogy. The entire pot of soup, that's the population. It's every single person or thing we want to draw a conclusion about. And that little spoonful, that's our sample, the small, manageable group we actually collect data from. The whole goal is to make sure our spoonful tastes just like the rest of the pot. And this is where the language gets a little specific, but stick with me, it's pretty simple. The true saltiness of the entire pot is called a parameter. It's a fixed value we really want to know, but we can't measure it directly. The saltiness of our spoonful, that's a statistic. It's a value we can actually calculate. See the pattern? We always use the known statistic to estimate the unknown parameter. But, and this is the absolute key, even if the chef stirs that pot perfectly, one spoonful is never going to be exactly the same as the whole pot. This natural variation isn't a mistake. It's called sampling error. I'm going to say that again. It's not a mistake. And pretty much the entire field of inferential statistics is just a box of tools to help us account for it. Okay, so we've got our spoonful of soup. Now what? How do we use it to formally state our guess about the whole pot? Well, there are two main ways. One is super precise, but probably wrong, and the other is a little less precise, but way more likely to be right. Just think about it like you're trying to catch a fish, right? A point estimate is like throwing a spear. It's a single, precise guess, like saying the average study time for all students is exactly 15 hours. I mean, what are the odds it's exactly 15.000 hours? Basically zero. And an interval estimate, on the other hand, is like casting a net. It gives a range, like the average is somewhere between 13 and 17 hours, which has a much, much better chance of catching the true value. So that net we're casting, that's what we call a confidence interval. It's a really simple idea. We take our single best guess, that's the point estimate, and we add a little cushion on either side to account for that sampling error we just talked about. And that cushion has a name, the margin of error. So you might be wondering, what determines how wide that net is? Well, three things, really. If you want to be more confident that you've caught the fish, you're going to need a wider net. If the data itself is just all over the place, you'll also need a wider net. But, and this is so important, the more data you have, the larger your sample size, the smaller and more precise your net can be. The bottom line is simple. More data gives you a better, more precise guess. All right, so estimating is great, but what if we want to do more than that? What if we want to test a really specific claim, like, does this new study drug actually work? For that, we turn to a process that, believe it or not, works a lot like a courtroom trial. The whole idea here is built on a principle you already know, innocent until proven guilty. In our statistical trial, the defendant is something called the null hypothesis. That's just the default assumption, but nothing is going on, that there's no effect. The researcher? Well, they're the prosecutor, trying to present enough evidence, enough data to convince the jury to reject that idea of no effect. And this isn't some random process. This trial always follows 4 clear steps. First, the prosecutor states the charges. They define the claim of no effect and the alternative that in effect exists. Second, the court sets the standard of proof, what counts as beyond a reasonable doubt. Third, we weigh all the evidence from our data, and finally, we deliver the verdict. So what is that standard of proof? Well, in most of science, it boils down to this one number, 0.05. We call this our alpha level, and it basically means we're willing to accept a 5% risk of making a mistake, specifically a 5% risk of a false positive, of convicting an innocent defendant. And the key piece of evidence we look at is something called a p-value. Now, the p-value answers a very, very specific question. If the defendant is truly innocent, if there's really no effect at all, how surprising is the evidence we found? So a tiny p-value means our results are really, really surprising, which, makes us start to doubt that the defendant is actually innocent. Now, just like in a real courtroom, the verdict isn't always right. Because we're only looking at a sample, not the entire population, we can make mistakes. It turns out there are 2 ways to get it right, and 2 very specific ways to get it wrong. Okay, first up is a type 1 error. This is a false positive. The easiest way to think about it is the fire alarm going off when there's no fire. In our courtroom, this is like convicting an innocent person. We conclude there's an effect, but we're wrong. And the probability of this happening is that alpha level we set just a minute ago. Then you have the type 2 error, which is the exact opposite. It's a false negative. This time, there is a fire, but the alarm stays completely silent. It's like letting a guilty person walk free. A real effect exists out there in the world, but our study just wasn't powerful enough to find it. It's a missed discovery. Okay, and this brings us to what might be the single most important part of this whole explainer. Let's say we run our trial, we weigh the evidence, and we get a guilty verdict. The result is statistically significant. Great. But what does that actually mean for the real world? It's the ultimate so what question. Just because we've proven that an effect is statistically real, that doesn't automatically mean it's big enough to be important. A statistically significant result is not always a practically significant one. See, statistical significance just answers one simple question. Is the effect real? Yes or no? But with a huge sample size, you can find a statistically significant effect that is absolutely tiny and meaningless. Like, imagine a new SAT prep app that raises scores by an average of just half a point. With enough students, that effect will be statistically real. But is it practically useful? Probably not, right? So to answer that bigger question, how much does it actually matter, we need a different tool. And that tool is called effect size. An effect size is a standardized measure that tells you the magnitude, the size of your finding. It's the difference between saying the drug works and saying the drug lowers blood pressure by a whopping 20 points. It gives us the context we desperately need to judge importance. And, that really is the big takeaway here. Good science isn't just about getting a simple yes or no verdict from a trial. It's about tasting the soup. It's about casting a wide enough net, and then being able to tell everyone, not just if you found something, but precisely how big and how important it really is. It's about describing our world with honesty and with nuance.